thanks for the invitation. I'll talk about stable giant complex structures and vibrations. So let me just get on with it. So first, the stable giant complex structures were introduced by myself and Marco Gualtieri, and kind of at the same time by Yushi Goto. And the idea is that whenever you have a giant complex structure, you can locally describe it by a pure spinor line. So you can pick a generator. And there is always a canonical section. So that's a generator for my spinor line. I can always project it into the complex numbers just by taking the degree 0 part of it. So there's like a canonical section of the anti-canonical bundle, which given a canonical section just takes the degree 0 part. So if that section is transverse to the 0 section, then I call it stable. So if you think of it, for symplectic structures, typically write it as e to the I omega. So for that particular generator, it would be starts with 1. So this section applied to that one would just give me 1 all the time. So the sigma here would be nowhere vanishing because I can apply to a section and just get 1 all the time. If it's a complex manifold, I'll apply to the complex volume form locally, and that there's no degree 0 parts to that, so I'll just get 0. So that section would be just 0 all the time. So in a way, the places where the sigma is non-zero are the symplectic locus of your giant complex structure. And we're asking that it fails to be symplectic in a very controlled way, namely it has this transverse vanishing. The typical example to keep in mind is this one I have here at the bottom. So essentially, it's something like a complex two-dimensional picture, which Marco kind of wrote something very similar to that already today. And then some symplectic transverse directions. So it really is kind of modeled on C2 with this specific giant complex structure, which has type change at z equals to 0, and symplectic for the symplectic direction. It's a very restricted thing. So that's what it looks like locally. There's no further ambiguity there. Technically, we can put a complex parameter here, which we'll do. So technically, we could put z plus lambda dz dw, but it's very simple. And why did we study these stable giant complex structures? First, because they exhibit this type change. So they're not purely symplectic, they're not purely complex, they have a bit of both. So that seemed like an interesting feature of giant complex structures that was missing in the standard cases. We thought that if you look at that, you'll be able to get interesting examples and interesting properties that are missing for like constant type cases. So that's what we did. And immediately, kind of right away, back in 2007, we already got examples in 4 dimensions. Like one of the early questions, does 3CP2 have a giant complex structure? And the answer was yes. And we kept on getting more and more examples. So, and they're all of this very simple, like we're putting the simplest type of type change, and you're already getting a whole bunch of examples of giant complex structures. And one thing that we kind of realized more and more as time went on is that you can use symplectic techniques to study these manifolds. So while the general case is like holomorphic Poisson, and as Marco was saying, holomorphic Poisson structures are a little tricky because there are too many conditions on them. It's difficult to really put a hands on them. These ones are very simple. So you can use symplectic techniques to understand them. But the way to get the symplectic techniques going is by studying the differential geometry of divisors. So sometimes they call them Loyenha pairs nowadays. So that's kind of the main point of it. Even if the giant complex structures themselves may be like a curiosity about giant complex manifolds, maybe the study of the geometry of a divisor is something that goes beyond just giant complex geometry. And one thing that I hope to is that this could be the language to redefine and compactify log labials. So this is something that people in more algebraic geometry study. It's the complement of a divisor, anti-canonical divisor on a Fano manifold. And it's like somehow the word divisor is already there, it's already complement. So it feels like we are kind of heading towards the same thing. And there's a number of similarities between what I say and what they do. Is this the same or not? So that remains a question. So let me just tell you about a few examples, because this was really the most successful way to produce examples. So S1 cross S3 was one that already appeared in Gualtieri's thesis. I think it's a stable giant complex in 2 different ways. But after that, we started getting more interesting examples because we were manifolds that were not complex or symplectic. So the first ones were these connected sums of CP2s. And I think most people do not know, but connected sums of CP2s is not complex. It's only complex when m is equal to 0. So only CP2 is complex, all the other ones are not complex. Connected sums of S2 cross S2 also are only complex for 1 connected sum. If you have more of them, it's not complex, but they're all stable giant complex. Elliptic surfaces are also example, and that's a little funny because if you pick an elliptically fibered K3, for example, it has a stable generalized complex structure with type change on something homologous to elliptic fiber. So that's like it's clearly not a caladial thing anymore. So that's a weird thing that you can do by doing surgeries. So like it really lives in another space. It's completely disjoint for the caladial structure on the K3 that we know about. And another thing that we can do is blow up. So of course, if you pick a point in the symplectic locus, you can always blow up a point there. But what I did with Marco was to pick a point in the singular locus where the structure is doing the type change, and there you can also blow up a point. And in fact, that blow up is canonical, different from the symplectic blow up that depends on a parameter. Here, when you blow up, you introduce a Lagrangian sphere of self-intersection too. One, it's a blow up. So that's like we can produce a whole bunch of examples. So essentially, if you pick these two families of examples you have here, you can keep on adding CP2 bars to it as well, as many as you like. So adding CP2 bars for free. There are a few shortcomings of these stable generalized complex structures. One of them is that you kind of, I think of them, you know, CP2 and blow-ups of CP2s. I think of that as like del Peso surfaces, and you might think that you can have that also in Fano varieties. And the fact that in higher dimensions that's not the case is a bit of a bummer, because I would like this to connect a bit to the study of Fano manifolds. And the other thing that's, even though in the previous slide I was telling you about all these manifolds which were stable generalized complex, the way we guessed that those manifolds are stable generalized complex was a little bit tricky, because we did a whole bunch of cut and paste and got something and say, this something I got is stable generalized complex. What is it that I got? And then maybe because of four manifolds, I can kind of go and figure out the diffeomorphism type, but it was not obvious. So it was like the diffeomorphism type came as a surprise. So that was a bit of a shortcoming. Why did we get the manifolds that we were getting there? So I would like to tell you about a whole bunch of things first, and I think that's the most important part is the 1 and 2, is just this geometry of a manifold with a divisor. So even if I forget about generalized complex manifolds, I think this is something that has room to be useful elsewhere. And then I'll start focusing on generalized complex manifolds. I'll talk about 4 dimensions. That's really where we get like get the best grip on the structures. And I'll try to give examples. I'll tell you about how to do connected sums, and then those examples cease to be a coincidence. It's just the fact that you can actually do connected sums of these spaces, which, again, like connected sums of CP2 is not complex. So connected sum is not a good operation for symplectic geometry. It's not a good operation for complex geometry, but somehow in dimension 4, it's actually good for stable generalized complex. I'll tell you a little bit about blow-ups and something about smooth manifolds as well, how to smooth out the certain things. And then I'll try to tell you about fibrations. I don't know why nodal trade appears twice there, but anyway. So look at that. Okay, so what I'm going to talk about today is, so I'm going to extend the definition of stable, and what I'll do is to remove the condition that the section is transverse, and just say it should be transverse with self-crossing. So that's what the X is doing that for you, is the Roman numeral with self-crossings. But I'm not going to be saying with self-crossings all the time, so I'll just do like that. I'll just call it stable. But from now on, the word stable means with self-crossings, and that means that if at some point there are no self-crossings and this like a zero locus of my divisor is actually smooth, I'll call it smooth. Okay. And for me, a generalized complex structure is stable if in appropriate coordinates it has this form. So the degree 0 part of the spinor is given by a product of complex coordinates. That, like, so the manifold itself doesn't have to be complex, but locally should be able to write complex coordinates at 1 up to zk, for which the spinor looks like that. So they are individually coordinated, can complete them to a coordinate system. The manifold itself is just real, so like the remaining coordinates can be just x1, x, etc.
So the manifold is not k-dimensional. It's higher.
No, it's higher dimensional.
It's
yes,
like 2k dimensions.
No, exactly. Yes. So like the highest number that can appear there is n, which would be the dimension of the manifold, and then you have actually just a collection of complex functions which give you coordinate patch in that neighborhood of that point. So why do we do that? I think Mark already kind of gave you an idea. So one idea is that, like I was saying, photos are not examples if you just impose the transversality condition, but if you allow self-crossings, you're in a much better situation. You can pick like CPN, for example. CPN. or 2n, and just pick this particular holomorphic Poisson structure and use that one to deform the complex structure. And you can see what happens to my spinner. I have to just active pi in the complex volume form. And what I see is that the linear part, the degree zero part of the spinner that gives me the holomorphic Poisson deformation, it's going to be Z1, Z2, Z3, Z4, etc. to Zn. So that would be the case in which you actually get all the products. And that means that this is like a self-crossing, as by the definition, going all the way to like certain points are really complex because the spinner just ventures up to the order. And okay, so that's nice for CPN, but then you can start picking, like for this particular Poisson structure, you can start looking at some complex submanifolds and see that they can be blown up. Like in the Poisson rule, they also understand when you can blow up submanifolds. And for example, the axis Z1 equals to Z2 equals to 0, something I can blow up, and the Poisson structure lifts to the blow up. So I can again get one of these stable transcomplex structures on the blow up as well with self-crosses. So this kind of clearly gives me more examples, because before CPN was not an example of a stable one, but now not only I can get CPN, but I can start doing all sorts of blow-ups and so on and get more examples. The same thing happening for a few funnels. So what's the geometry that kind of is behind this? So I'd like to put my hands on these stable complex structures, and the language to that is the language of divisors. So first thing is just complex divisors. That's what you get associated with a complex line bundle. And again, so here I just cross the X because I'm not going to be talking about self-crossing complex divisors. For me, all the divisors will be self-crossing from now on. And the way to go about doing this, at least differentiably, so I have no holomorphic structure going on here, okay? That's an important feature. If you give me just a complex line bundle, which for some reason is called K star over a manifold, and I have one of the sections here which is transverse to the zero section, and self-crossings, I can form the ideal. I can form the ideal of like pairing that particular section with anything the dual bundle, because I started with K star, I'm pairing things on K now. And I can just see, so this is an ideal on the space of smooth functions. And I can look at the vector fields which preserve, the complex vector fields which preserve that ideal. And that turns out to be a locally free sheaf. So this is all the vector fields which preserve the ideal, and I get something which is a locally free sheaf. That's just computation that you do. And then it comes from a vector bundle. So we kind of start to introduce some notation. The zero locus of my section is called D for the divisor, and the actual bundle is called TM log D. And I think we normally call that the complex log tangent bundle of N. Okay, D, because of the self-crossings, is a immersed submanifold with transverse intersections. It's good to see it in local coordinates, just have an idea of what you're talking about. So locally, if I have a trivialization, the signal would look like this product of coordinate functions, complex coordinate functions. The ideal is going to be generated by those coordinate functions. I have just the ideal generated by the product Z1 of ZL. And then you can go on and figure out what the generators of that bundle is in this particular coordinate. And you get this kind of thing. So in the holomorphic, there is no complex structure around, but in the holomorphic directions, you do get Z1 DDZ1 up to ZL DDZL. So those preserve the ideal. The bars, you don't have to put any coefficients of that. So DZ1 bar kills the ideal, kills the generator, so it preserves the ideal. And you have the remaining coordinates that are just real coordinates here. And that altogether should give me the generators for this particular space. So I have a few generators which are, if I try to think of them as vector fields, they are vanishing vector fields at some points, but as far as generators and relations, this gives me a vector bundle with a projection map onto the tangent space. So that's a Lie algebra. And you can look at the dual bundle, so that's the space of forms. So whenever you have a Z to the Z, you get a D log as the dual guy. And so you have a few D logs up to L, that's the number of generators of my complex divisor there. And then I have the DZ bars, they appear normally, and also all the DXs appear without any coefficients. So this is the kind of thing, if I was to write forms, complex log forms, I'm allowed to use D log Z up to D log ZL, and D of the remaining coordinates. But it's interesting to see just that the D log Z and the DZ bar, they appear in different ways. So that they have like different weights, right? So you have to do something about that. But then
what does that mean? So you're really describing the complexified
So
Lie algebra, right?
it's a complex Lie algebroid. So like it's just that I think what's coming out of this that does not come from a real Lie algebroid, and that's why you think like if you have this Z bar, then you should also have this Z. But it really is just a complex Lie algebroid. So there's nothing at this stage that it's real of, right? It's complexification of. And it's good to have like an example that's a bit less trivial. So S4. One thing you can do in S4, so S4 is just 2 copies of C4 glued by the inversion, and this is the inversion. If I want to keep it orientation preserving, I have to put a bar somewhere. So the bar is here, just so that the orientation of the coordinates W1, W2, and the orientation of the coordinates Z1, Z2 actually agree when I do the gluing, right? And then I can look at the function, which is Z1, Z2 on the Z coordinates, and W1, W2 bar on the W coordinates. And when I do this gluing, the ideal, so the ideal they generated, the functions don't get meshed, but they don't have to. I just have to generate the ideal, and that's fine. So that gives me a line bundle, gives me a log divisor on S4. And the picture would be that you have your S4, and you can look at the 0 locus of this ideal. So it has like one circle and has another circle, which unfortunately I think I just have to do it like this. And they intersect each other. That's the with self-intersection, intersect each other in these 2 points, like at 0 and at infinity. Okay, so that's a bit of picture I can get here. And one thing that turns out to be important is that like these functions Z1, Z2, they give me co-orientations for the circles. So if I also look at say this point here, which says the Z chart, Z side, when I look at Z1 equals to 0, the function Z1 gives me a co-orientation on the normal bundle of that guy in the same way that Z2 gives me a co-orientation on the normal bundle of the other one. So both of these guys on this chart are co-oriented in a way that kind of is compatible with the orientation of S4, right? So this Z1 with Z2 together, they were chosen so that it was compatible with the orientation of S4. On the other side, I'm in the W coordinate chart, and I can also look at the generators, but now it's ZW1, W2 bar. So they do give me co-orientations, but the co-orientations are like the W1 is fine, but the 2 has a bar. So like the if I try to kind of put the co-orientations together to look at an orientation of the total space, it would not agree. So there is like something that's positive about this side and negative about this side, right? So somehow it's whether or not the co-orientations that the ideal is giving me for the different strands of the divisor coming in, whether those co-orientations actually give me the orientation of the ambient space or not.
You were saying circles there, but are they spheres?
They were spheres, but this S2 here was an S4. So yeah.
Yeah, no, I get
sorry,
yeah.
I meant spheres that intersect at 2 P1s intersecting at 0 and infinity, so to speak.
And these are the 2 complex.
It's all complex. Yeah, exactly. They're complex. Yes, yeah, I'm lacking of 4-dimensional drawing skills. Anyway, so like once you have this language in place, then it just becomes a matter of looking at these structures, and then you see that actually this is supposed to be B plus I omega. That stable Giles complex structures with self-crossings correspond just to B plus I omegas, so complex forms in this Lie algebroid. With the property that if I take D of that, I should just get the 3-form H that we were talking about just before. So this the twist of the current algebroid. And that is the imaginary part. So like here, I should have really written, it was I changed the slide last night and I forgot imaginary of B plus I omega, which really is just omega. It should be non-degenerate. So just the imaginary part of B plus I omega is non-degenerate. There's no further condition on B. B could be whatever. Okay, so there is an pointwise algebraic condition on omega. And there is just one a bit of an annoying thing here, which is that, which kind of gets the whole thing started, which is taking the imaginary part, like even though we look at it and we understand, because you're writing to B plus I omega, it all makes sense that it's a singular forms. The Lie algebroid was complex Lie algebroid. There's no real imaginary part. So like this guy here is not a form on that Lie algebroid when I take the imaginary part. So like there is the question of where does it live then? So it has to be something real associated to the Lie algebroid, which is not the Lie algebroid itself.
So the imaginary part is not degenerate and closed, right? Because
yeah, it's closed. This being closed kind of comes from this condition here, right? So
yeah,
like
yeah.
the real part is d of b is h, and d of omega is b0 from that condition over there. So that's kind of what makes us go into the world of elliptic divisors. Like, what is this real thing that somehow contains the imaginary part? So that's where should I be looking at? And the idea is that you should be looking at things that are locally generated. So you pick a collection of Morse-Bot functions for codimension 2 submanifolds, you product them together, and the condition I have on this codimension 2 submanifolds that they should look like this intersection of complex manifolds. So they should intersect themselves transversely again. So that this F1 up to FL should look like norm of Z squared. So before I had this function Z1 up to ZL, and now this F1 FL should look like norm of Z squared instead of Z. So they are real thing that somehow contains the information of some of the information of the complex divisor. And then you can again play the same game. So once you have these functions defining the submanifolds, you can look at the vector fields which preserve the ideal generated by this F. And again, it's going to be locally free. So it's again going to be sections of a vector bundle, and you give it a name. And the name is just the same one as before, but now you have this kind of a absolute value around D, and you call that the elliptic tangent bundle. Okay, so but now the F is a real function. This X is actually real vector fields, and this is a real Lie algebroid. Okay. If I was going to write this in local coordinates, I could write each F as I say norm of Z squared, so something like that, you know, norm of one coordinate square plus the next coordinate square, so Ri squared. And if I'm in a neighborhood, I can think of it as these are like these two variables are kind of parameterizing a copy of R2, and I can think of the radial direction and the angle direction that is going around, so preserving R just by rotations. So that's what these theta's are. And then if I look at my generators, they look like this. Up to L, I have the Euler vector field in the direction of that variable and the rotation in that hyperplane. And then at some point, I just get continuation by further variables that have nothing to do with this story. Okay. And similarly, if I want to write what are the one forms that I'm allowed to use, I'm allowed to use d log R, I'm allowed to use d theta for all of them. And then I have the remaining dx1 of dx, and they are not really contributing much to this part. So for example, if I was to complexify things, I would have like d log z1 is equal to d log r1 plus I d theta 1. And then you see that like once I start complexifying these objects, I will be able to write all sorts of generators also for the complex tangent bundle. Except I do not get to write dz1 bar. Dz1 bar is not there. So what's going on in this case? So how do I go from complex to elliptic? These two things are related. And the idea is that to go from complex to elliptic is easy. If you had that section that I talked about, you can pick sigma bar, which would be a section of the dual bundle, multiply them together, that becomes a function that has the correct behavior, because one of them has all the z's, the other one have the bars, so it becomes precisely a Morse function with z1 squared, z2 squared, etc. So from the data that gives me a complex divisor, I can produce one of these elliptic divisors, and the imaginary part of a form actually is just a map from the complex to the elliptic. So that's where the symplectic form, the thing that is actually interesting, the one that's actually giving me the Johnson complex structure, it lives in here. And then you might ask yourself, like, can I go backwards? So does every elliptic divisor, every elliptic tangent bundle comes from a complex tangent bundle by this procedure? And does every symplectic form on the elliptic tangent bundle come from a complex one? So like, so the idea is that I would like to be able to look at symplectic forms on this space, and somehow if I find that they exist, I'd like to be able to conclude that I get a generalized complex structure because it's kind of symplectic on that space. So that's a bit of the name of the game. I'd like to relate the generalized complex geometry to symplectic geometry here. Okay, so that's first question. Does every elliptic tangent bundle come from a complex tangent bundle? And the other one is about the symplectic forms. Do they come from a complex one? So there are two questions I'd like to answer. The first one has a simple answer, which is like if you look at the function defining the divisor, even if you look locally, it's a bit like an R squared, so it's Z times Z bar. And all that you need to be able to go from R squared to Z is to decide like which one do you pick, Z or Z bar. So that's just the coorientation. So if you have, so if you give me coorientations, so this is a stratified space, right? Because it's a bunch of self-intersections. So just look at these move parts, like the codimension, complex codimension one part. If that part is coorientable, then you can actually start picking the Z coordinates, and you do come from a complex log tangent space. It's funny that like the further intersections, like the lower strata, the lower dimensional strata, they don't contribute to the answer to this question at all. And next thing is about the symplectic structures. Does every elliptic symplectic structure come from a complex one? And then we can start looking, like in the space of forms, I can write my elliptic form like that. So I just single out the singular generator. So here have, when they have two of them merged together, and here just the log, and here just the theta. And they'll have coefficients. So like, for example, this coefficient here, if I look at it over the divisor, that's a well-defined quantity. And if I come from a complex one, that quantity should be 0. So like this part here has to vanish if I come from a complex form. Because here, essentially, this is the coefficient of d log z, d log z bar. That's what this guy here is. And in the complex one, the d log z bar was not there. I could use dz bar, but not d log z bar. So this coefficient here has to be 0 if I come from a complex divisor. But if I start having intersections, then there's more singular coefficients that I can look at. For example, here I'm just looking at two forms. I can put R1 and theta 1 together. Oh, became an eraser. I can put R1 and theta 1 together, for example. But I can start mixing them up, not just like things that come from a single strand. I can have R1 that's coming from strand 1 and theta 2 from strand 2, or R1, R2 with the logs and so on. So there are 6 different things that I can put there. And if I'm looking at degree 2 form, I get 6 constants that appear here as these coefficients. So there's not only do I have this guy here, which would be defined on the smooth locus and has to be 0, but also when I start having intersections, I have to make sure that there'll be these guys here are compatible with being complex. So the question is like, what is the image of this map going from the complex log forms to the elliptic one? And this is a bit complicated if you think in general, because it's a bit like, you know, what's the imaginary part of Z1 times Z2 times Z3, like describe it in terms of x's and y's. You know, it becomes like a bit of an annoying polynomial to write down and describe in general, but for degree 2 forms, I really actually can do that. So for degree 2 forms, I can just write down the product. So here is the product actually is relevant. So I pick the d log Z1, which is this guy, d log Z2, put some complex coefficient in front and multiply them together. And what I get when I look at the imaginary part is that I get this term and this term. So the a's and the b's, I can separate them. And I see that the b is going to be the coefficient at the same time of the d log R1, d log R2, and d theta 1, d theta 2. So I have to have this, there's a minus sign there. So the coefficient of d log R1, d log R2 should be minus the coefficient of d theta 1, d theta 2. And similarly for R1, d theta 2, and so on. So if I have something that's coming from complex and goes to log, the 2 forms that I'll get will have automatically some matching of residues that would not happen if I just had a generic 2 form on this side here. Okay. So that ends up being the condition. So if I already have a complex divisor and I have a 2 form which is elliptic, but so like here I already have the complex divisor is given, and somehow I'm looking at the underlying elliptic divisor that comes out of that. Then there are 2 things that I need to have. One of them, in this move part, the residue. So the coefficient of d log Z1, d log Z1 bar, that one should be 0 in this move part. And whenever 2 strands come together, I need to have this coincidence of residues. If I have that, then I know that my symplectic form comes from the complex one, and therefore it is a generalized complex structure. So right now I'm in the business of looking for symplectic structures on this elliptic tangent space, which have this matching residues plus vanishing of the residue in this move part. Okay. And that's the theorem, like there's a bijection. So like if you have that, you really are done. So if you have, there's a bijection between stable generalized complex structures and oriented elliptic divisors with elliptic symplectic forms with 0 elliptic residue, this part, and matching mixed residues as in these 2 equations here. So this is really all you need to do if you want to put stable giant complex structures with the self-crossings in your manifold. So there is just this one annoying thing. Let me just do the recap.
Can you say again what elliptic means?
Elliptic is the real one, if the absolute value. So like when you have the complex line bundle, you do L tensor L bar and sigma tensor sigma star. So that gives you the elliptic one. So like just by the real function, Morse bot on the subscript manifold. Okay, so like in terms of generators, I think that's the easier one way to remember. In terms of the generators, where is it? Oh, yeah, it was easy to remember, but not easy to get there. So this is the elliptic. It has the Euler vector fields, which are real, and the rotation vector fields, which are also real. So the elliptic is kind of the real place where you can actually do geometry. And it's independent of choice of which one is Z and which one is Z bar. Right.
But the picture is always you're going to have a GCS and a codimension to submanifold, or
yeah,
singular.
Singular, yeah. Okay. Yeah, so that picture remains. So in the end of the day, I'm getting stable giant complex structures. Now, like before, you had always this smooth, like typical elliptic curve, and I can have these things which are a bit more complicated. So technically, if I'm looking for examples, which I am, I'm also making my life easier because I seem to be looking for something more general, right? So instead, I made the question easier, and now I can find an answer, right? So like before, I wanted to have something smooth, and I'm saying, I'll have all sorts of singularities. Can I get more examples when I do that?
But it's called elliptic because the defining function is like x squared plus y squared. It's not because it's an elliptic curve.
Right, that's right. It has nothing to do, like it's in dimension 4, these elliptic curves do come about, but it has nothing to do with that indeed, yeah. So just recap. There are two questions that we're kind of trying to answer here. One of them is, when does an elliptic log tangent bundle comes from a complex log tangent bundle? And the answer was, as long as the smooth part of the divisor is coriented, I get that. So for every choice of corientation, I get a different complex divisor that does the trick for me. So like there's a bunch of choices here that give me different complex divisors mapping to the same elliptic one. And when does the elliptic symplectic form come from a stable one? So if I actually manage to produce a symplectic form on this elliptic road, when is it giant complex? And there were two things, which was the zero elliptic residue and the matching of mixed residues. And the annoying thing is that the matching of elliptic mixed residues depends on orientation, because it involves the coefficient of θ1, for example, d θ1. If I change the orientation, then that changes by a sign. So matching will kind of get out of all of end. Because of that, it's kind of useful to have like an intermediate step in which you kind of allow for some, give yourself some leeway. So these are the elliptic residues that come from a complex, as argued before. But if I also change the orientation by hand, so I have picked the wrong one, then I'll get all sorts of signs changing. That's what I'll get. So somehow they do come from complex divisors, but maybe the wrong one. So this would be like if I had something like d log z, d log z2 bar. That's the kind of residues that I'll get below. And here is more like the kind of thing that we are really thinking about, d log z1, d log z2. That was the computation we did. So like, because of this choice of orientation, if I just have something on an elliptic and I have to start picking orientations by hand, maybe I'd like to consider them both in case I picked the wrong one. So I could go back and say, I'll fix it later. So the plan of attack is precisely that. I first try to find a locally complex symplectic form. So locally complex is if it's either of these two forms here, right? I try to find one of these locally complex symplectic forms, and then I start playing around with these orientations to see if at some point I can make everything consistent. So there'll be some signs that I get every time they intersect. And every time I change the orientation in one place, I change it in somewhere else. Like these things typically come like as spheres with self-intersections, like that. And every time I change the orientation of a sphere, so if I change that orientation here, that will affect two signs. It will affect the sign of this intersection here and of this intersection here. So I have to kind of, every time I change one orientation, I can fix a sign in one place at the expense of another. And then you see that like, if there was an even number of minus signs, even number of unmatched orientations, all come out fine. If it was an odd number, then not. And then let's just have here a simple example, CP2, because that's like the standard one. You can pick this d log z1, d log z2. That was the one we started with as well. And look at it, like where are my divisors? So z1 equals to 0 is a divisor, z2 equals to 0 is a divisor, and the line at infinity is also a divisor. So I end up with like 3 lines intersecting pairwise like that. It's all complex. So the complex structure actually is giving me the orientations. So they automatically compatible with the complex orientation of the whole CP2. So I like it's all matches, and we kind of know that because this was the example that Mark was also talking about of complex structure, or pretty close at least, complex structure on CP2. So this is all like all good. I'll put +1s here, and +1 just means good. So it means this matching of orientations with the orientation of the ambient space. So this one is a clear example of a stable generalized complex structure. We knew that before anyway. A more interesting one is this one. So I can take Z1, Z2 bar. So when I put the bar on the Z2, what I'm doing is picking something that has the opposite orientation, okay? And the bizarre thing is that this one, if I start looking at what happens if the line at infinity, it actually just extends as a symplectic form to the line at infinity as well. So this one still has a CP2, still has the same lines, namely Z1 equals to 0, Z2 equals to 0, and the line at infinity, they're all singular locus there. And I see that like at Z1 equals Z2, so like at the bottom here, the co-orientations, the Z1 is fine, is a complex one, but the Z2 has a bar. So like the co-orientation does not agree with the complex orientation of CP2, but if I look at CP2 bar, that's kind of how I define the orientation with the other one, right? So here I do get like a +1. And then I have these 2 guys here, and then you have to go into a computation, and like I think you get a -1 and a +1, or the other way around. So for some reason, you do end up with a -1 there. So it's not like the matching doesn't work, and there's no way that I can like, because whenever I change one orientation, I flip the sign in 2 places. There's no way to fix this and make this into a stable generalized complex. But it does have an elliptic symplectic form with kind of nearly all the properties that you want. Is locally complex, looks kind of good, zero elliptic residue and everything, but it doesn't come because of this minus sign here. There's a singularity problem at one of the vertices there. S2 cross S2 does the same thing. It has 4 lines, 4 divisors, and it's all compatible with the complex structure. So you get +1s everywhere. So it's an example of a stable generalized complex structure. A more interesting example is the one that had the divisor on the 4 sphere. So here there were 2 lines, right? So 2 S2s that intersect at 0 and at infinity. And the question is there a symplectic structure on this space? Welcome to the symplectic S4. Yes, it does work. You start with this one here, which was compatible with the orientation that it had in S4. So that gives you a plus sign on one of the sides, but they intersect again at the other side. And as we observed, like it has this bar here, and then it doesn't. So like it's a +1 and a -1. So in that picture I had before, which was like this sphere, 1 line, and the other line somehow I'll just draw it bigger again here. So one side gives me a +1, and the other side gives you a -1, and it's a 0 residue, 0 elliptic residue, and locally complex elliptic symplectic structure on S4. What this is telling me is that like S4 is nice because at first, like spheres don't have no right of being symplectic, so the other thing that's nice is that the gluing map from Z to the W was just inversion on the disk, right? Once you start getting that the inversion on the disk is a symplectic map, that means that if you find a place that looks a bit like this, you can remove that neighborhood, invert the disk, and glue it to something where the structure looks a bit like that. So you can do connected sums. Like if you think a bit, why can I not do connected sums of symplectic manifolds? Because if I could, I'll be able to pick the same map that I used to glue the big parts that the one you're interested in. You'll be able to get the disk that you're removing and glue to the other disk that you removed in a symplectic manner and get a symplectic structure on this sphere. And that's a big no-no. But now that you have a symplectic structure in S4, obtained by using this inversion map, you can actually do the same thing, but instead of gluing the sphere, gluing the complements, and you get a connected sum operation. So it's a big theorem here. The only thing that I would like, so okay, there is a connected sum. What can I do connected sums of? First, I need to have this strata that intersect. So that's this part here. Say that I have a manifold, and I didn't leave myself space to draw. I have here my manifold, and I should have a divisor on the manifold that looks like that. It has this cross here. Here I should also have my manifold and a divisor with a cross here. So I need to have these points that are in the intersection of two things. And this is in 4 dimensions, 4 manifolds, okay? Another thing is there is the whole business with co-orientations, and here I should have a +1. Here I should have a -1. If I do that, then I can actually just keep the co-orientations I had before, glue them along precisely small disks around these points, and I get now an elliptic symplectic structure, which all the co-orientations are the ones I had before. If for some reason I had a +1, then I kind of have to play around with co-orientations, then it's not going to be a canonical choice that I get in terms of co-orientations in the connected sum. But that's the business here. You can always get elliptic symplectic structures on the connected sum, and whether or not the co-orientations will agree or not depends on whether you have pluses and minuses or pluses and pluses. So for example, we already knew that CP2 had stable transcomplex structures. We know that CP2 bar has that one with a -1. We know that S1 cross S3 that we don't know anything about. S2 cross S2 also has some transcomplex structures with a bunch of +1s, right? So it's kind of these 4 lines intersecting. So now I can start gluing them together. And if I have a -1, it's all good. If I have a +1, then I have to flip all the sign or something and go from there. But that's the thing. And one interesting thing is like if you pick CP2, which was this, or CP2 bar, for example, which was these 3 lines with +1, +1, -1. Like when you think of connected sums, we tend to think of 2 manifolds separate and then you glue them together. But it doesn't have to be like that. You can just pick 2 points on the same manifold, remove a small disk around each one of those points and glue. That's attaching a 1 handle, but that's also connected sum. And in this case, for example, of CP2, I have here the -1 point, I have the +1 point, and I can cancel them out. I can actually glue and get something which would get, it becomes something like this. So unfortunately, I cannot really do the drawing properly because these are the lines going through or something, but it has like a divisor, like this line here will become a divisor that does not intersect the other one because now I kind of glue things together. So it becomes 2 separate divisors in something that looks a bit like that. This one continues like that as well. Okay, so that's you can do this connected sums, and that's when you start getting this kind of spaces here, connected sums of S1 cross that's attaching 1 handle to your space. Another thing that is interesting is that you can do blow-ups. We kind of have been studying that for a long time now. But what do you need to actually blow up a submanifold? And if you're in a complex geometry, you kind of say, well, if you give me a complex submanifold of coordination more than 1, then you can blow up. But in these move worlds, like you think of symplectic blow up, that always seems to depend on some choices that you make, because you have to make the normal bundle something. So blow up can be made canonical as long as you have a collection of complex functions defining that submanifold. So if you think of the complex divisor, that's what is given you. The complex divisor is defined to you by saying I have complex functions that cut it out. So whenever you have the intersection of 2 strands or more of the complex divisor, you have a bunch of complex functions defining that intersection. So you can blow that up canonically. Okay, so you don't have to kind of pick a small ball, bigger diffeomorphism or anything. There's a canonical way, there's a canonical blow down there. And if you look at elliptic divisors, that's a bit more interesting. Because, okay, so if you can get these orientations, you make it a complex divisor, and in the complex divisor world, you can just blow up canonically. If you have different orientations, you have a different complex divisor, different ideal, you can still blow up canonically. So there's no canonical blow up in the elliptic world because these orientations can change what you're doing. But any of those will give you a canonical blow up. So once you fix orientations, you can do a blow up and it's canonical. And even better, if you start looking, so the blow up is something that's happening down here at the manifold level. So M tilde is always the blow up, and then you have the blow down map there, or the derivative of it. But if that map lifts to the elliptic tangent bundle, and the nice thing is that even though like here, we know that the blow down map, like the whole, and if it has tangent to the exceptional divisor goes to 0. When you go to the elliptic, that ceases to be the case. The map becomes a fiber-wise isomorphism. So whenever you have something on the elliptic tangent bundle of M, you can just pull it back to the blow up. No matter which orientation you picked, you can just pull it back. Okay, so now it starts to become much less weird or like, yeah, I don't know how to say this. We are getting all this structure on CP2 plus CP2 plus CP2. Like, what is that? I already argued that we can do connected sums, so that's one reason to see it. We can blow up with the reverse orientation. So that is like adding CP2. And the only thing that happens is that we still have, like, we pull back to get the zero residue, elliptic, symplectic form, whatever. And the only thing that you're left with is checking if those residue conditions, if they were going to match in each of the vertices. And it turns out that when you do the blow up, it messes up, so you have to do twice, and then it's good. So that's the result. So given an arbitrary choice of orientations, we can blow up higher strata of elliptic divisors. The blow down map is a fiber-wise isomorphism for the elliptic tangent spaces. And the canonical, this means that there are canonical pullbacks of forms on the elliptic on the base to the elliptic on the blow up. And one thing that I was talking about before is like, it looks like I kind of cheated and went from smooth, which is where I wanted to find my examples, to non-smooth self-crossings. But we also proved that if you, in 4 dimensions, whenever you have the self-crossing, you can always smooth them out. There's something that also this first guy, Pim and Schedler, proved in more general case for holomorphic Poisson manifolds. But in 4 dimensions, you also have that you can always smooth out. So if you have self-crossings in 4 dimensions, you can just remove all of them and get back to the standard one that Marco and I were looking at many years ago. So introducing self-crossing in 0 dimension does not increase the number of manifolds that I get as an example, but now makes it simpler to see, like the blow-up procedure, the connected sum procedure, and so on. And I have no idea when I have to stop. It's 1 o'clock?
Yeah, it was, yeah, in 10 minutes.
In 10 minutes, okay.
Could I ask a question about the previous slide?
Yeah.
So when you take this normal crossing degeneracy locus and you smooth it out with this theorem, is there options? Do you have options?
Good question. I don't remember now, because we kind of just it's Z1, Z2 equals to 0, and you just put equal to epsilon and match these trends. Epsilon, of course, could be 1. It's like at first I'll think that not. At first I'll think not.
Okay. But you could smooth some of the
Yeah,
intersection points and not others.
That's right. Yes, that can be. It's a local construction, which maybe in other cases when it's holomorphic, it's less clear. But like this is a local construction that can smooth out points individually. What's this slide? Okay. And you're going to get back to that. So the thing that kind of got us interested was also this vibration picture. So first one is just a boundary vibration, which is, so the idea is that with a vibration map, well, vibrations are very nice and so on, but we would like to allow the vibration map to have some singularities. And a typical one that people like to put is left-shed singularities. That goes well with symplectic geometry. They're also like ciphered fibers. You can also put, so some have a bit more singular central fiber that's covered by nearby fibers. Would like to put this type of singularity here, in which the first 2 coordinates get mapped into things like that. So it's a one that appears if you are familiar with like manifolds of torus action type of thing. Okay, so this is what you call a boundary vibration, and I'll just like to take a look at what this map looks like if I just had 4 coordinates, for example. So why is it called boundary vibration? So here I'll have Z1, Z2, which like just going here. So Z1, Z2 is like Z1 is given by X1, X1, Y1, and Z2 is X2, Y2. And the map is just picking this and mapping to norm of Z1 squared, norm of Z2 squared. So it's picking the whole C2 here and mapping just to this top quadrant here, right? So it's automatic. The image gets a boundary, becomes a manifold of corners. So that's why we call this a boundary vibration. So outside of this is a proper vibration, but over these guys here, there seems to be some singularity, but the fact is that if you put the correct tangent space on the base, which is called the B-tangent bundle, it's actually a subversion of Lie algebroids also at the boundary. So there's something that goes on here that becomes like it behaves like a nice submersion. So it makes sense to call it a fibration as well. And the standard example are manifolds with torus action. So if you have Tn acting on a manifold with double dimension, then the quotient is a boundary fibration. And here just required to have no finite isotropies because you don't have deciphered fibers up here. That's what they are. You could have, just didn't want to have them. And on top of that, there's also another type of singularity that people often do, which is this Lefschetz singularities, which is when you have complex coordinates. Note that the manifolds here are not complex, but to define a Lefschetz singularity, you kind of assume there are complex coordinates which render your singularity of this form. Like if your manifold didn't come from a complex geometry setting, it's kind of, or if you didn't put the singularity there by hand yourself, it's kind of difficult to actually prove that something is a Lefschetz singularity. And for me, a boundary Lefschetz fibration is one that has either of these two types of singularities, either this type of thing, and I'm always in 4 dimensions again, or the previous one with the boundary type of vibration. So elliptic means just like it's just keeping track of how many variables are in this elliptic part here. So elliptic means just one pair, x and y. Elliptic means 2 pairs, so x1, x1, y1, x2, y2. And the Lefschetz one, because I'm in 4 dimensions, I don't have elliptic. So now that you have all the singularities in place, you can think a little bit about what happens with vibrations, so the evolution of vibrations. Thurston proved back in the days that if you have a symplectic vibration, you can put a symplectic structure in total space. Symplectic vibration over symplectic base. You can put a symplectic structure in total space, and you just pull back the structure from the base, add a symplectic structure from the fiber, kind of have to make sure that there's a closed form that does that for you. And if you put big enough of multiple here, if you put this K here big enough, then this thing becomes non-degenerate and you get a symplectic manifold. Years later, Gomp realized, okay, you can kind of repeat the same thing, but allow for Lefschetz singularities. And I kind of repeat the arguments away from the singularities, but near the singularities, I kind of tweak things by hand so that it's still symplectic, and I glue things in a compatible way so that in the overlap, it works fine. And what I did with Ralph was to allow for the elliptic ones, so just the ones that don't have only one complex variable and Lefschetz singularity. And that looks an awful lot like Landau-Ginzburg models that people do in mirror symmetry for funnels. So there they have the elliptic divisor, they have the complex divisors, and they have maps that look an awful lot like these ones that we're looking at. So there seems to be a connection.
So when you say elliptic, do you also mean elliptic?
Sorry, this really means elliptic. So the boundary here did not have corners.
Yes.
Yeah. So
that was my question.
That's what exactly, yes. So the boundary here did not have corners. So here typically, if we're to draw the boundary of this vibration, it would look like this, which is the boundary, and there could be some Lefschetz singularities inside. Actually, this is the picture for CP2. There's 3 Lefschetz singularities inside and a boundary around here. So that's vibration over the disk. And here you have like so like now the next question is, what if I have this elliptic one? What if I have these corners? Is it the same thing? It's kind of the same, but like it's good to just think a bit about what's happening. If I just was to pick C2, R2, standard projection map that I was writing before, symplectic form on the base, which is like log, so it's all fine. Pick a symplectic structure on the fiber, which is something like, this one here, I guess. And then try to do the trick. And then what's going on is that I have to pick K large enough for it to be symplectic. But once I pick K large enough for it to be symplectic, I don't get the matching of the residues. So like the matching of, like before it was nice because being symplectic is an open condition, so I can add a large multiple and I get there. But now I don't have this possibility of adding a large multiple because it spoils the closed condition of having matching residues. So what you have to do is just be careful, just like what Thurston was doing for the Lefschetz singularity. You kind of have to go there by hand and tweak around each of the vertices and make sure that you keep the residues matching after that, and make sure that in the overlap, you didn't spoil anything. So that's what we did. So if you have like one of these boundary Lefschetz vibrations, manifolds with corners and everything, you can actually put a stable giant complex structure on it. In fact, you can even do one for which the parameter of d log z1 wedge d log z2 is just a complex, an imaginary number. In principle, it could have a plus lambda a plus ib, and you can do it in a way that is just the ib. So no further a. So for CP2, just to kind of come back to the examples we're looking at, we all know that CP2 has this moment map, right? So it's like has a T2 action and have moment map, and this is the picture. So now this is not the lines that are crossing, it's just the image of the moment map. And this is a boundary left chat vibration in this new setting. So this gives me a trans-complex structure on CP2 with this particular divisor being the 3 lines. CP2 bar is the same manifold, has the same action. So it's all good. It's the same thing. And the only problem is that now I don't get the matching of the residues again. So it's good to keep track of the signs. The only thing that you have to make sure still is that we chase the signs back. So this one will again be +1, +1, -1, and then it doesn't work for Giants complex, but it is stable, like has a 0 residue elliptic. S2 cross S2 again is this picture. Now this is just because I can rotate, S1 rotates one S1, the quotient is an interval, as the other S1 rotates the other one, gives me an interval, the product of 2 intervals is the square. So all groovy, all complex, you get a bunch of +1s. But like from this example here, I had 3 sides. From this example here, I have 4 sides. So and we know that if you blow up fixed points for circle actions, you get more sides. Do I have something less sides? Do I have something 2 sides? Yeah, that's S4. S4, if you remember, I had like it can rotate the Z1 coordinate, can rotate Z2 coordinate, and the fixed points would be when both of them are 0 or both of them are infinity. So the quotient of S4 by the standard torus action is just a diagonal like that. Which again, there's just this problem, which is a +1 here and a -1 here. But it has one of these boundary left chat vibrations with a elliptic symplectic form, and you just have to keep track of the sign again. So another nice feature is that connected sums can be performed also preserved in a vibration preserving manner. Okay, so from these examples that I have here, I can not only do the connected sum that I described before, but I can even do it in a way that preserves the vibration structure. So I can start picking these examples here and just adding them together to get fibered Giants complex structure. So for example, I could do the CP2, which was this example here, CP2 bar, 1, 1, -1. I could glue this vertex here to this vertex here to get these manifolds. And now this is really the base of a vibration with a +1 here, and that is just CP2 bar connected sum S1 cross S3, I think. Another thing that we managed to do was what's called a nodal trade. So that's something that I learned from a paper of Leonis Minto that Marco told me about. But it goes in mechanics by the name of Hamiltonian Hopf bifurcation. And the idea is that you can actually, whenever you have the situation here in your vibration, so here is the rest of the vibration. Whenever you have a vertex like that, you can push it in, and then you move out this corner, and you create a left chat singularity inside. So you can go for that. That's what I was talking before. If you have self-crosses, you can remove the self-crossing and smooth everything out. You can also do that in a vibration preserving manner. So if you have a vibration, you can get your elliptic divisor, so you can pick all the corners of your vibration, push them all in, and get something with the disk and a bunch of left chat singularities inside. You can also go backwards in the appropriate circumstances and pick something which has a bunch of left chat singularities. It's therefore kind of difficult to understand. Push them outside and get something which just has corners but no left chat singularities inside. That normally is what I think physicists would call the large structure limit. When you start with a complicated thing, but in the end it's like just C or some power of C. And there's one question that we keep on getting, which is like, what about the Euler characteristic of these spaces? So somehow we keep on getting them with positive Euler characteristic. And there's a reason for that. If I have a vibration like this, with some edges and some left chat singularities, the way that these things work is that each one of these guys here will contribute with +1 to the Euler characteristic. Each one of these guys here also gives me a +1 to the Euler characteristic. And otherwise, there's no further contribution. So like to find the Euler characteristic, I have to do just sum a bunch of +1s. In the best case, I'll have no vertices outside and no left chat singularities inside. and then I'll have Euler characteristic 0. But from that, I just get positive Euler characteristics. So because all my manifolds are described eventually by these vibrations, at the moment, we do not have any examples with negative Euler characteristic. That's something that Rafael Torres already was mentioning a while back. Like, are there any examples with negative Euler characteristic? It seems to be a bit of an issue with the tools that we are using, because they have this lack of ability of changing the Euler characteristic of what you started with, and it typically started with something positive Euler characteristic. But it's a genuine question. Are there stable transcomplex structures with negative Euler characteristic? We do not know. And that was the end of it. Sorry, I went over time. Any questions or comments for you?
So okay, so these boundary Lefschetz vibrations, which have singular fibers at the boundary and perhaps at some points in the interior. So, is it possible that you could have such a boundary vibration over a diagram like this, which is not embeddable in the plane, which is in, let's say, a higher genus Riemann surface?
Yes, yes, for sure.
And is it possible that that's where you might get negative Euler characteristics?
So let's see here. Because the issue, I think, is something like this. Let me try to. Because you can always pick all the singularities and bring it to some point, right? So it might be, but if I remember correctly, that it is something like this. Have you here a Riemann surface? And let's say I have a boundary here with a few kinks, right? I can pick all my singularities, Lefschetz singularities, and put them here, and kind of cut out this part here. Okay. So I can look at because the other characteristic has this additive property, right? So I can to compute the other characteristic of the whole thing, I can consider first this part, and then the intersection. In this part, I just have a torus vibration, so that has a 0 Euler characteristic. And then the intersection is going to be again a new manifold, so it has 0 Euler characteristic, and I'm left with just the Euler characteristic in this cylinder here, with some kinks as well. So it doesn't look like vibrations would do the trick for me, even if I allow for a more general base. Like, we kind of keep on insisting on the disk, but it doesn't have to be the disk. We can even have some that I think we can flip to orientation.
More the vibration structure.
Yeah, exactly. Yeah. Further comments or questions?
Yeah, I have a question. So, do these stable GCS and also the more generals that you are considering, the ones, do they occur in generalized scalar structures or?
Yes, they do, right? So the example in S1 cross S3, like all these examples that Mark was talking about as well, like typically the Poisson, like being stable is this holomorphic Poisson by vector, right? Like if you started Kähler in the form by holomorphic Poisson structure, if the holomorphic Poisson by vector was stable, so that we had 0, which was transverse, like was transverse to 0 section, not power transverse to 0 section, then this is stable. So the example that Mark was giving earlier today, which was Z1, Z2, DZ1, DZ2 type of thing, that's stable. So the examples that we have for S1 cross S3, or for the D group S1 cross S3 is stable. If you start looking D groups in higher dimensions, then the D group structure starts playing up, and I have no idea, those are probably not stable, but I did not check.
And did you think of whether there are some special metrics which are adapted to this stable GCS? How do they interact with this device?
For the generalized scalar structure.
Yeah,
I was wondering the same thing with Marco's talk, actually, if somehow like he's doing everything on the tangent space and somehow introducing the elliptic tangent bundle and trying to repeat the constant rank case, but in the elliptic tangent bundle would be something. I do not know. But then like it would still be very specific, because I think what he's aiming for is like the general holomorphic Poisson case, and if you can, like, that's more interesting. But if that doesn't have a solution, then maybe the stable case and changing the algebra from the tangent to the elliptic tangent problem like that. So that helps.
So if there are no further questions, let's thank Gil again. So let's meet in 5 minutes at the